here is the question. And as with a lot of A-level maths questions, particularly the pure questions on Unit 1 and Unit 3, it's quite short as written on the page. There's not many words, there are not even many symbols, and yet for this short question you're being offered a relatively generous 6 marks. The first thing to do is to decide what the question is about, and in short questions like this you need to look for a key word. I would suggest that the key word here is this one. This being an equation, the usual course of action in GCSE and A-level is to solve the equation. You should be aware that that's not quite always the case, but in this case we're very explicitly being asked to solve the equation. Okay, what sort of equation is it and what are the difficulties with this equation? Well, for a start, the unknown, which here is written as theta, it's an angle, appears in 2 places, one on either side of the equation. That's one potential difficulty. The other difficulty is that there are 2 different trig functions appearing in the equation. Now you've got to decide which of these 2 difficulties is the most significant, because that's normally the one that you will have to address first. This being an A-level question, it should occur to you that the issue with the trig functions is more A-level-ish and more significant than the issue with the unknown appearing on both sides. Okay, so let's deal with the trig functions. Okay, 2 different trig functions. How do we deal with an equation which has 2 different trig functions? There is a standard procedure here, and that is to apply a trigonometric identity. The trig identity that we need in this particular case is what's called the fundamental trig identity. It's the most basic trig identity. It might be at this stage the only one that you're aware of. I can guarantee you there are lots more trig identities to come, but in this case this is the one that we need. You should be aware where this trig identity comes from. We're allowed to quote it in this question, but in other questions we might, for example, be asked to prove this trig identity. You should also be aware of the geometrical significance of this trig identity and how it relates to Pythagoras' theorem. So in our case what we're going to do is we're going to use this identity to substitute for the slightly more complex of the 2 trigonometric expressions in the equation. That's the one on the left hand side, so we need to rearrange the trig identity like this. Okay, so cos squared theta equals 1 minus sine squared theta. So let's go ahead and substitute that into the original equation, so replacing the cos squared theta on the left hand side. This gives us an equation in which theta still appears, the unknown theta still appears twice, but now there's only one type of trig function, the sine function. We now need to do a little bit of tidying up on this equation. First, we're going to expand the brackets. You probably would have thought of doing that anyway. And then we're going to do just a little bit of shuffling around of the terms. I'm going to do 2 simple algebraic steps to leave me with this. You should make sure that you understand which 2 algebraic steps I've done. Slightly trickier is, why did I do those 2 particular steps? The hint here is that I've left the right hand side of the equation as 0 now. That should give you a big clue as to where we're headed with this one. We've now got to address the second of the 2 issues with the equation, which is that the unknown theta still appears twice. There are usually 2 interpretations to this particular aspect of an equation. It could be that it's a linear equation in which the unknown appears twice, and we'd know what to do with that on the basis of fairly basic GCSE maths, GCSE grade D or E or something like that. But this is the other of the obvious options, which is that what we've got here is a quadratic equation. Okay, here's the equation again. You may or you may not recognise this straight away as a quadratic equation. To make the connection a bit more explicit, what most students would do at this point is to replace the sine theta function with the unknown x. So the equation would now look like this. If you're a bit more confident, you might have done something a little bit smarter perhaps, which would be to replace the sine theta term with the letter S. It's up to you which letter you use for your new unknown. We sometimes refer to this kind of thing as an auxiliary variable in an equation. If you're more confident still, you might be happy to avoid this step altogether and just to proceed with a quadratic equation in the variable sine theta. But in any case, it's probably best to write it like this, like the way I've got on the screen here, as that's what the examiner will expect to see. So we now have a much friendlier looking quadratic equation in a simple variable x, no trig functions appearing. At this stage, you need to show that you're proficient in how to solve quadratic equations. Well, first things first, again, basic GCSE stuff, you should look to see if the equation factorizes. Does it factorize? Well, in this case, yes, it does. What you'll find in Unit 1 questions on this particular topic is that, certainly from past experience, they do generally seem to factorize. Now, I can't guarantee that that will always be the case for you. So, if it does not factorize, there are two options. Either you've got to do something different by way of solving the equation. So, for example, completing the square, or if you prefer, using the quadratic formula. The other option is that it's possible that you have made a mistake. One tiny little error in one of the coefficients in the quadratic equation, just maybe a sign error, a plus or minus sign error, might lead to a quadratic equation which does not factorize when it should factorize. That's going to be a significant problem for you, so you need to do your algebra very carefully. But anyway, no problems here. This equation factorizes, and from the factorization I can deduce that either one of those brackets must be 0, from which I can get the two possible solutions for x for my quadratic equation. Either x is negative 1/3 or x is 1. Okay, at this stage we need to go back and put this in terms of theta. Remember, x was an auxiliary variable that we introduced to help us to present a solution of the equation. The examiner didn't use the letter x, so we've got to go back and put it in the terms that the examiner set. So x simply represents the quantity sine theta. So I'm going to write that last line back in terms of theta. Okay, so instead of having x equals negative 1/3 and x equals 1, I've now got sine theta equals negative 1/3 and sine theta equals 1. Each of these is what we call a simple trig equation. Not a quadratic trig equation, but a simple linear trig equation involving just one trig function, which is the sine function in this case. Let's carry on in the obvious way now. Let's invert the sine function in each case. So theta is either the inverse sine of negative 1/3 or the inverse sine of 1. And again, let's just take the obvious approach here is we'll just use our calculator to tell us what the values of theta are. So in the first case, we get theta is negative 19.47 degrees, and in the second case, theta is 90 degrees. You could have worked out the second case, obviously, without a calculator, but in any case, your calculator will tell you that the second solution here is exactly 90 degrees. The first solution is an awkward decimal, and you've got to make a decision on how you're going to round that decimal. I've just noted that in the examiner's mark scheme, they go for 2 decimal places here, so let's stick with that, 2 decimal places. Okay, moving on. Let's go back to these two solutions. If we were naive, we'd stop at this point and we'd lose a whole bunch of marks. We've now got to use some of the properties of the trig functions. There are 2 properties of the sine function that we need to use to generate the appropriate solutions for this equation. First is what we call the symmetry property of the sine function. The symmetry property of the sine function tells us that whatever our calculator gives us when we do this inverse sine function, The other solution related to that by symmetry is 180 degrees minus what your calculator told you. Okay, so in the case of theta equals negative 19.47 degrees, another solution is 180 minus that, which is 199.47 degrees. And corresponding to the original 90 degree solution, 180 degrees minus that, well, in that case, that's also just 90 degrees, so nothing new there. So, having a look at what's on the screen here, I've got 3 distinct, that means different, solutions. And at this stage, I should call them potential solutions still, because I still haven't sort of tied it in with certain details in the question. So 3 distinct potential solutions, negative 19.47 degrees, 90 degrees, and 199.47 degrees. We've now got to use the second important property of the sine function, which is its periodicity property. You will remember that the sine function is periodic with period 360 degrees. Here is how we need to use this fact. Here are the 3 solutions from the previous slide. The periodicity property of the sine function tells us that I can add or subtract any integer multiple of 360 degrees to or from each of these 3 solutions. That will generate 3 doubly infinite families of solutions, like this. Here I've used the ellipsis symbol, the ... symbol, to indicate that each of these sequences, each of these 3 sequences is doubly infinite. Okay, it starts sort of from negative infinity and carries on up to sort of positive infinity. Okay, so at the moment we have 3 doubly infinite families of solutions. That's a lot of solutions. Okay, the original solutions from the previous page are just highlighted there. Okay, the trick is now to highlight which of these solutions are the ones that are relevant to the question. And to identify that, you need to look at the very last part of the question in the top line there. It wants only the solutions between 0 and 360 degrees. So I'm going to look carefully at my list of solutions here and I'm going to highlight the ones that we want. There we go. It's just 3 of them. It will be polite at this point to write your answers out in ascending order. Okay, it's not the examiner's job to pick out the solutions from your whatever you've scribbled on your page. You've got to get into the habit of presenting things in an examiner-friendly way. So there we go. I've picked out the 3 solutions and written them in numerically ascending order: 90 degrees, 199.47 degrees, and 340.53 degrees. And that's the complete solution to this particular question. Let's review some of the core skills that we needed to display, we needed to demonstrate to the examiner in order to successfully complete this question. Number 1, algebraic manipulation. There's not many A-level questions that don't require a certain level of algebraic manipulation. Sometimes it will be fairly basic, sometimes more advanced. In this question, you may remember we had to do a little bit of shuffling around with the equation. We had to expand brackets, we had to move terms around. And then at a slightly more advanced level, we had to show proficiency in the solution of quadratic equations. Next, a specifically A-level skill was we had to show the examiner that we understood the fundamental trig identity, sine squared plus cos squared equals 1, and we knew how to implement this. And then, at a later stage of the question, we had to show an understanding of trig functions and how to solve simple trig equations. This required us to use the inverse trig functions or the inverse trig function on our calculators, but also to employ the symmetry and periodicity properties of the trig functions. It was the sine function in this case, In other questions, you will have to show a similar understanding of the cosine function or possibly the tangent function. And it's because of this, these levels of difficulty, the algebraic difficulty, quadratic equations, and the properties of the trig function, that you will inevitably get multiple solutions in a question like this. The examiner is very much trying to find out, have you got the right number of solutions? Now, it's possible in other versions of this question you might get more than 3 solutions. It is possible you could get fewer than 3 solutions. Okay, but I would suggest that in questions like this, 2 or 3 or 4 solutions would be fairly typical. Let's take a look at some of the wider skills that we used in the question and some connections which aren't really necessary for the solution of this particular problem, but will help you to link things in with other parts of the syllabus. Firstly, we use what I call the fundamental trig identity. Sine squared plus cos squared equals 1. Where does this come from? Well, trigonometry, when you first learned about it at GCSE or possibly in Year 9 maths, is to do with right-angled triangles. Here's a right-angled triangle in which I've assumed that the hypotenuse has length 1 unit. I've labelled the lower of the 2 acute angles, the acute angle at the right-hand side of the base, as theta. So in this triangle, basic trigonometry, B grade GCSE trigonometry will tell you that the adjacent side of this triangle would be hypotenuse times cosine of the angle shown. So that's 1 times cosine theta, so that's just cos theta. And the opposite side would be hypotenuse times the sine of the angle shown, so that's 1 times sine of theta, so that's just sine theta. Okay, if we combine that little bit of GCSE B grade trigonometry with some GCSE C grade Pythagoras theorem, we know that the sum of the squares of the 2 shorter sides is equal to the square of the hypotenuse. So if I just write that down, I will get that. So that's why the fundamental trig identity is sometimes called the Pythagorean trig identity. Now, the problem here is that I've only proved that this is true when theta is an acute angle. In a right angled triangle, the 2 angles that are not the right angle must be acute angles. So it's a bit of a cheat, and I haven't really proven that it's true for any angle theta, but in fact it is. Okay. Another connection, you might at this point, those of you who are familiar with the type of question that we've been working on, be a bit baffled that I haven't used anything to do with graphs. Okay, I didn't show a trig graph and I didn't use a trig graph to get me to a solution. That's because personally I don't find trig graphs very helpful for a question like this, but you might. So let's take a look at this. If we go back to step 3, we were faced with solving 2 simple trig equations. Here's where trig graphs can be useful when solving simple trig equations. So if I were to draw suitable graphs for each of these equations, they would look like this. Okay, the left-hand graph shows the sine graph in blue and y equals negative 1/3 in yellow. And the right-hand graph, again, sine graph in blue and y equals 1 in yellow. So the left-hand equation, the solutions of the left-hand equation correspond to the intersections of the 2 left-hand graphs. So the first of those, the one that my calculator gave me, is this value of theta. Okay, now if you remember this was negative, you can see from the graph it's negative, and that's why it didn't appear in the final solution. The 180 degrees minus that solution is this one here. That did appear in our final solution, and the periodicity solution, the periodic solution, the one that's 360 degrees plus the negative calculator value, is there. So those 2 solutions appeared in my final solution, those being the only 2 intersections between 0 and 360. The other equation is a bit simpler because the only intersection, the only place where the graphs touch here, is this point, and that was theta equals 90 degrees, and that was the 3rd solution. Okay, but of course you can never read exact values or accurate values from a graph, but it might just help you to visualize the symmetry and periodicity properties. More useful, I think, in terms of understanding the trig functions is what I call the circle diagram. You may be familiar with this under the name the cast diagram or the ASTC diagram, but the cast or ASTC is just a small part of it. I think the circle diagram contains a lot more than that. Here's a typical version of the circle diagram. What we've drawn here is the unit circle, circle of radius 1, centered at the origin. Okay, and I've drawn one particular radius of the circle. The radius I've drawn makes an angle theta with the positive x-axis. Theta, in fact, is a measure of turn. So in this diagram, theta can be allowed to be an angle bigger than 90 degrees. Could be an obtuse angle, could be a reflex angle, and could even be negative if I allow an amount of turn which is clockwise from the positive x-axis. Okay, again, similarly to my previous diagram, the adjacent side of the right angle triangle I'm showing is cos theta and the opposite side is sine theta. Okay, so for the purposes of this question, we were interested in the sine function. The sine of an angle is the vertical, the opposite side of this triangle. Or put another way, more usefully, the sine of that angle is the y-coordinate of the end point of the radius. So the angle shown here is, let's say, it looks like about 70 degrees. Okay, the sine of 70 degrees is just a little bit less than 1, we can see from here. Okay, the symmetry property of the sine function can be demonstrated like this. I've drawn another radius here, a dotted radius or dashed radius, and that's in the position where the angle from the measured from the positive x-axis is 180 minus the angle I've shown there. So, 180 minus about 70 degrees. So the new radius is at an angular position of about 110 degrees. You can see that the y-coordinate at the end point of this radius is the same as the y-coordinate at the end point of the original radius. So that's indicating in the circle diagram that sine of theta is the same as the sine of 180 degrees minus theta. That's how the symmetry property of the sine function is displayed in this circle diagram. You may also want to think about how the symmetry properties of the cosine and tan functions are shown in the circle diagram. That might be for another time. And how the periodicity property of the sine and cosine functions are shown in the circle diagram.